Good evening, everyone. So this is the lecture number 2 for the motion along a straight line. In the last lecture, we discussed about the velocity, acceleration, and the average velocity and average acceleration, and also we discussed about the position vector displacement and average speeds also, right? So, but in this lecture, we'll be further discussing about the velocity and acceleration in component form, right? We'll be discussing the velocity and acceleration in Cartesian form, in vector form, right? So let's suppose that we have this Cartesian coordinate system. This is our Cartesian coordinate system, XYZ system, right? This is our Cartesian coordinate system, right? This is our y-axis and this is our x-axis. And let's suppose that we have a particle P here. The particle is at position P, right? And the position of this particle is given by this position vector, right? That's drawn from the origin of this Cartesian coordinate system. And this is nothing. OP is the position vector, right? We can denote this position vector by this R vector, right? And let's suppose that the coordinates of this particle P are nothing. These are x, y, and z, right? These are the coordinates of this particle, and the particle is in a space, right? It is in a three-dimensional space, correct? So the coordinates of this particle will be given by the x, y, and z coordinate, right? So we can write this r vector will be written as, it's nothing. This is equal to xi cap plus yj cap plus zk cap, correct? And let's suppose this particle P here is not at rest, it's having some motion, right, in some directions. And this particle P is moving, right? It means that the x coordinate, y coordinate, and z coordinate are also changing for this particle, right? So if x, y, z coordinate are changing, it means that the particle will be having a velocity along x, velocity along y, and velocity along z. It means there will be three components for the velocity for this particle, right? So we know that velocity is nothing. It's equal to it's the rate of change of position vector with respect to time, right? So it will be dr vector over dt, right? So this velocity is rate of change of position vector over time. We can replace this position vector with d over dt of xi cap plus yj cap plus zk cap, right? So it will be nothing. It will be d by dt of, it will be dx upon dt I cap plus dy dt j cap and dz over dt k cap, right? So our velocity vector will be nothing. That will be equal to dx over dt will be nothing. It will be the component of velocity along x direction, so it will be vxi cap. And similarly, we will have vyj cap. And finally, we have vzk cap, right? So these are the three components of the velocity along x, y, and z direction. And from here, if we have to calculate the modulus of this velocity vector, right? Means if we have to calculate the speed, right? Speed will be nothing. It will be mod of v, and it will be given as under root of vx square plus vy square plus vz square, right? So this will be the speed of this particle, right? This is how we will calculate the magnitude of the speed of this particle, right? And similarly, if some force, we know that velocity is changing for this particle, the velocity is a variable here, right? All the three components of velocity are variable here. It means that there will be acceleration along all the three directions, y, x, y, and z, right? So we'll try to find the acceleration also here. So acceleration is nothing, it's given by the time derivative of velocity vector, right? So it will be d over dt of v vector, right? We can replace this v vector with vxi cap plus vyj cap plus vzk cap. So this will be our acceleration, or we can say that dvx upon dt is nothing. It's equal to axi cap. It's equal to axi cap plus ayj cap plus azk cap, right? So we can rewrite it as our a is nothing. That's equal to axi cap plus ayj cap plus azk cap, right? So this is nothing. This is our acceleration, right? ax is the component of acceleration along x, and ay is the component of acceleration along y, and az will be the component of acceleration along z direction. And similarly, if we have to find the modulus of this acceleration vector, that will be given by nothing. That will be under root of ax square plus ay square plus az square, right? So that's the magnitude of this acceleration vector, right? So that's how we will calculate the magnitude of the acceleration vector, right? So in the component form, we represent the position vector of this particle, right? We also represent the velocity in three component forms along x, y, and z, and acceleration also along three components, right? X, y, and z. Let's try to calculate the displacement for the particle. Let's suppose that if a particle, let's take again the same. Let's draw a Cartesian coordinate system here. We'll be having this or y, x, z, right? And let's suppose that particle was initially at position P, right? At position P, and if at this coordinate, if at this position the coordinates of P are x1, y1, and z1, right? And let's suppose this particle changed its position to some point P, right? To some point P, and at this point the coordinates of this particle are x2, y2, and z2, right? These are the coordinates of this particle, right? So the position vector of this particle, this is the initial position vector, right? For this particle. And this will be the final position vector, right? This will be the final position vector. That means that this is our RF vector and this is our RI vector, right? Initial position vector. We can write RI vector as x1 I cap plus y1 j cap plus z1 k cap, right? And we can also write this final position vector as x2 I cap plus y2 j cap plus z2 k cap. And our displacement vector will be nothing. It will be RF vector minus RI vector. That will be x2 I cap plus y2 j cap plus z2 k cap minus x1 I cap minus y1 j cap plus minus z1 I cap, z1 k cap, right? Z1 k cap. So it will be x2 minus x1 I cap plus y2 minus y1 j cap, and finally we'll be having z2 minus z1 k cap, right? So this is nothing. This is our delta r vector or displacement vector, right? So this will be our displacement vector. And the magnitude of this displacement vector will be nothing. It will be once again the same. In the same manner, we'll be calculating the magnitude of this displacement vector. So it will be nothing. It will be under root of x2 minus x1 ka whole square plus y2 minus y1 ka whole square and z2 minus z1 ka whole square, right? So this is how we will calculate the magnitude of displacement vector. If the position vector of a particle if the two position vectors of the particle are given in the component form, right? So this is the magnitude of a displacement vector, right? So all these concepts now we'll be using to further solve some of the questions related to motion along a straight line. We'll be using all these concepts to study the motion along a straight line. Will be calculating the velocity, acceleration, position vector, displacement, and many more things, right? So all the concepts will be used in solving some of the good problems, right? Let's start with the question number 1, right? This is our question number 1. The question 1 says that a cyclist moving on a circular track completes a 1 revolution in 10 seconds, right? Let's suppose that this is our circular track here. This is the circular track here. And on this circular track, the cyclist is moving and is completing 1 revolution in 10 seconds, right? We can say that the time period for this revolution for this motion is nothing, it's equal to 10 seconds, right? Means in 10 seconds, the cyclist completes 1 complete revolution. Then find out its displacement after 1 minute 5 seconds, right? The radius of this track is given as 1 meter, right? The radius of this track is given as 1 meter. We have to find the displacement after 1 minute and 5 seconds. So we'll try to find the number of revolutions, right? How many revolutions the cyclist complete in this time, right? So it will be nothing. Our time is given as we'll just divide time with the time period. The time is given as 1 minute and 5 seconds. It means it's 65 seconds, right? 65 seconds over 10. So it means that it's nothing. It's equal to 6.5 revolutions, right? So 6.5 revolutions. So this number of revolutions are being completed by this cyclist, right? In 65 seconds, right? It means that the cyclist, if the cyclist starts from point A after 6 revolutions, the cyclist will be again at the point A, and then it will once again complete the half revolution. So after 6.5 revolutions, the cyclist will be exactly at this point B, right? It will be exactly at this point B. So the displacement will be nothing. The displacement is the shortest distance between initial and final position, right? We can see that the displacement here is nothing between A and B. It's nothing. It's equal to the diameter of this circle. So the displacement for this question will be equal to nothing. That will be equal to diameter of this circle. That's nothing. That's equal to 2 meters, right? So 2 meter will be the answer for this question, right? So after 6.5 revolutions, the displacement of this particle from its initial position will be equal to 2 meters, right? So let's move on to the next question. The next question is that we have been given a position vector, right? A position vector of a particle varies with time t according to the law. It's given that the position vector of this particle is varying like it's t square over 2 I cap minus 4 over 3, and it's t to the power 1.5. We can write it as 3 over 2 j cap plus 2t k cap, right? So this is the position of the vector of a particle, right? Where r is in meters and t is in seconds. Find suitable expression for its velocity and acceleration as a function of time. So we have to find the velocity as well as acceleration as a function of time. We know that velocity is nothing. It's equal to tr vector over gt vector, right? And we'll differentiate this r vector with respect to time. So we'll be differentiating this position vector with respect to time. It will be nothing t square over 2 I cap minus 4 over 3 t to the power 3 over 2 j cap plus 2t k cap. So we'll differentiate this vector, this position vector, to get the velocity as a function of time, right? So it will be nothing. Differentiation of 2 square t square will be 2t, and there is 2 in the denominator, so we'll be left with it's 2t square upon 2. It will be 2t upon 2, right? The derivative of t square over 2 will be 2t upon 2 minus minus 4 over 3, and the derivative of 3 raised by t raised by 3 over 2 will be nothing. It will be 3 over 2 here, and t raised by 1 over 2, right? We'll have I cap here, right? This is the I component of this velocity, right? We'll be having I cap here and this is j cap here, right? And finally we'll be having 2t square over 2 k cap, right? So this will be our velocity vector, right? 2 and 2 will go, 3 and 3 will also go, 2 and 2 will also cancel out, this 2 and 2 will also cancel out. We'll be left with t I cap minus 2t over 1 by 2 j cap plus t square k cap. So this will be our velocity vector, right? So this is the velocity as a function of time if the position vector of this particle as a function of time is given like this, right? So similarly, we can calculate the acceleration from this particle. Acceleration will be nothing. It will be dv vector over dt. So it will be equal to d over dt of this velocity vector, right? That's t I cap minus 2t j cap plus t square k cap, right? So in this here that the z component of the position vector was 2t, right? And the differentiation of 2t will be 2, not t square, right? Can just write to t here. It will be t here, correct? Now the differentiation of t is nothing. It will be equal to 1. So we'll be left with I cap here. The differentiation of this t raised power 1 by 2 will be 1 over 2. T over minus 1 over 2. That will be j cap. And the differentiation of this just a minute. It will be t here, right? It will be only 2 here. We'll be having 2 k cap here. So also here it will be 2 k cap. And it will be 2 k cap here as well. So it's 2 k cap, right? So we'll be left with, and the differentiation of this 2 k cap is nothing. It's a constant. It will be equal to 0, right? So this 2 and 2 will again cancel out. We'll be left with I cap minus t to the power minus 1 by 2 j cap, right? So this will be the acceleration, right? This will be the acceleration of this particle, correct? The second part for this question is find the magnitude of its displacement and distance traveled in the time interval t equal to 0 to t equal to 4 seconds, right? We have to find the magnitude of its displacement. We have to find the magnitude of displacement. In the part second, we have to find the magnitude of its displacement and distance traveled in the time interval 0 to 4 seconds, right? And we know that displacement is nothing. It's given by the final position vector minus the initial position vector, right? So position vector at time t equal to 0, that's given by t square over 2, that's I cap, minus 4 over 3, that's t to the power 3 by 2 j cap, and then we have z component that's given as 2t k cap, right? So the initial position vector will be nothing. We have to put just time t equal to 0 in this case. So it means that at time t equal to 0, the particle will be at 0 position, means the particle will be at origin, right? And after time t equal to 4 seconds, the final position vector will be nothing. It will be 4 square over 2 I cap minus 4 over 3. 4 is for 3 by 2 j cap plus 2 into 4 k cap, right? So it will be 16 over 2, that's 8 I cap minus 4 over 3. 4 is for 3 by 2 j cap plus 8 k cap, right? So our displacement vector will be nothing. It's the delta r vector that's equal to final position vector minus initial position vector, right? That will be equal to initial position vector is 0, right? That's a null vector. So it will be 8 I cap minus 4 over 3 into 4 3 over 2 j cap plus 8 k cap, right? And we can also find the magnitude of this displacement by just taking the under root of x component square, y component square, and the z component square, right? Let's move on to the question number 3. A train travels from city A to city B with a constant speed of 10 meter per second and returns back to city A with a constant speed of 20 meter per second. Find its average speed during its journey. Let's suppose that a train is traveling between the two cities A and B. From A to B, the velocity of this train is, let's suppose it's v1, and from B to A in the reverse direction, the speed of this train is v2, right? And let's suppose the distance between A and B, that's given as s. S is the distance between the two cities. And let's suppose that time t1 is taken by this train from A to B and time t2 is taken by this train from B to A, right? So our average speed is nothing. Average speed is nothing. It's the total distance over total time, right? So average speed is nothing. It's total distance over total time. The total distance during this journey from A to B, from B to A, from A to B, the total distance is again is equal to s, right? And from B to A, it's also equal to x, so it will be s plus s over the total time, that's t1 plus t2, right? So it will be 2s over t1 plus t2, correct? And the time taken from A to B will be t1. That will be distance over the speed, that's v1, and t2 will be distance over the speed, that's s over v2, right? We can substitute the value of t1 and t2 in this equation. So the value of the average speed will be nothing. It will be twice s over v1 plus s over v2, right? So s and s will get cancelled. So it's nothing. It's 2 over 1 over v1 plus 1 over v2, right? Or we can write it as twice v1 v2 over v1 plus v2. So this will be the average speed in this case. We have been given that the v1 is given as 10 meter per second and v2 is given as 20 meter per second. So average speed will be nothing. That will be equal to twice 10 into 20 over 30, right? So average speed will be nothing. It will be 40 over 3 meter per second, right? And remember one thing, average speed will always lie between, it will always lie between v1 and v2, right? So it cannot be less than v1 or it cannot exceed v2, right? So 40 over 3 lies between 10 and 20 meter per second, right? Let's move on to the question number 3. Question 3 says that position of a particle traveling on a x-axis is given by that x is given as t cube, right? It's a function of time, that's t cube. Find position of a particle at time t equal to 2 seconds, right? After time t equal to 2 seconds, for part A, the position will be after time t equal to 2 seconds. So position will be nothing, it will be 2 cube, right? So it will be 8 meters, right? It will be 8 meters, correct? And after it, we have to also calculate average velocity from t equal to 2 seconds to t equal to 3 seconds, right? Between t equal to 2 seconds and between t equal to 3 seconds, right? So let's talk about the part number second, right? So we have to calculate the v average, but this time we have to calculate the average velocity, right? So average velocity is nothing, it's the total displacement for total time, right? our displacement is nothing, that's delta r vector, that's nothing, that's equal to final position vector minus initial position vector, right? Our final position vector will be nothing, it will be t cube at time t equal to 3 seconds minus t cube at time t equal to 2 seconds, right? So this will be our displacement, right? So delta r vector will be nothing, it will be equal to 3 cube, that's 27 minus 2 cube, that's 8, that will be equal to 19, right? So the value of the displacement here is 19 and the time taken is delta t, that's between 3 and 2 seconds, so it will be 3 minus 2, that's equal to 1 second, right? So V average is nothing, total displacement, that's 19 over total time, that's 1. We can say that 19 meter per second is the average speed or the average velocity, not average speed. And we have to also calculate in the part C velocity at time t equal to 2 seconds. The velocity at time t equal to 2 seconds in the part C velocity at V at time t equal to 2 seconds, right? So V will be nothing, it will be dx over dt. So it will be d over dt of t cube, right? That will be equal to 3t square, right? 3t square. So V will be nothing, that will be equal to 3t square, but we have to calculate time t equal to 2 seconds, so it will be 3 into 2 square. So it will be 12 meter per second, right? So 12 meter per second is the correct answer for this part C, right? So let's try to discuss another question. It's the question number 4, right? Question number 4. The velocity of a particle is given as velocity has been given as 2t square minus 4t, right? Plus 3. Find its acceleration at t equal to 2 seconds. So acceleration will be nothing. It will be dv over dt, right? dv over dt. So it will be d over dt of 2t square minus 4t plus 3. So it will be nothing. It will be 4t. So acceleration will be here 4t minus 4 plus 0, right? At time t equal to 2 seconds. So 4 into 2 minus 4. So 8 minus 4, that's equal to 4 meter per second, right? So 4 meter per second will be the acceleration of this particle, right? Now let's move on to the question number 5. Question number 5 is one particle having velocity is given as under root of x plus 1, right? It's given as under root of x plus 1. We know that we can write acceleration as dv over dt. We can also write this acceleration as dv over dx multiplied by dx over dt, right? It will be the same, right? It won't change. So we'll be left with dx over dt is nothing, it's v velocity, and dv over dx is nothing, it's the slope between v and x graph, right? So our acceleration, we can write it as, our acceleration is either dv over dt, or we can also rewrite it as v dv over dx, right? Correct? Here v is given as under root of x plus 1, correct? Under root of x plus 1. If v is given as under root of x plus 1, we can write it as v square will be equal to x plus 1, right? V square is equal to x plus 1. So differentiating both sides with respect to x, right? With respect to x. So it will be 2v dv over dx, correct? 2v dv over dx, and dx, our dx will be 1, and the differentiation of this 1 will be equal to 0. So from here, our v dv over dx comes out to be equal to 1 over 2, right? That comes out to be equal to 1 over 2. So this v dv over dx is nothing, it's our acceleration, right? It means the acceleration is nothing, it's 1 over 2 meter per second square, right? It's a constant acceleration equal to 1 over 2 meter per second square. So that's how we can find the acceleration if the velocity is given as a function of position of a particle, right? So this is our question number 6 here. The position of a particle is given by, our position is given by x is equal to 6t square minus t cube, right? Then find out its position when velocity becomes maximum, right? We have to find the position of this particle when the velocity becomes maximum. Velocity becomes maximum means the acceleration becomes zero, right? At maximum velocity, acceleration is zero, right? So we can say that at maximum velocity, dv over dt is equal to zero, or acceleration is equal to zero, right? Or acceleration is zero, right? What we'll be doing is that we'll be finding the time at which the acceleration is zero, right? And then we'll substitute the value of time in the equation of x. We'll get to know about the position of particle when velocity becomes maximum, right? So our v is nothing, that will be equal to dx over dt, right? Dx over dt. So it will be 60 square. Our differentiation of t square will be 2t, so we'll be left with 12t, right? And the differentiation of 3 t cube will be nothing, it will be 3t square, right? And we have to put this equal to 0, right? So from here we can get 3t as common, right? 3t as common, we'll be left with 4 here minus t, right? That will be equal to 0, correct? So from here we get the two values of time, where the acceleration, where the velocity, from dx by dt we get the velocity, right? We don't have to put the velocity equal to 0, we have to put the derivative of the velocity equal to 0 to find the point, to find the time where the acceleration is maximum, right? To find the time where the acceleration is maximum. So this is our velocity. We'll be once again taking the derivative of it. We'll be calculating dv over dt, right? So dv over dt will be nothing. It will be 12. Differentiation of 12t will be 12 minus 6t square, right? 3t square, the differentiation of 3t square will be minus 60, right? So it's minus 60. So we have to find the time at which the velocity is maximum. If the velocity is maximum, acceleration will be equal to 0. That's dv over dt will be equal to 0. Correct? That's our 12 minus 60. So from here, the value of time comes out to be 12 over 6. That's equal to 2 seconds. So after 2 seconds, the velocity becomes maximum or the acceleration becomes 0. And from here, we can find the position after which the velocity becomes maximum at time t equal to 2 seconds, right? So it will be 6t square minus t cube. With the value of time here equal to 2 seconds, right? We'll be getting 6 into 2 square minus 2 cube. That will be 4, 6, that will be 24 minus 8, right? It will be nothing, it will be equal to 16, right? 16 meters. So the position of this particle when the velocity will be maximum or the acceleration will be 0 will be x is equal to 16 meters, right? This is our question number 7, right? The question 7 says that the relation between time and distance is given as t is equal to alpha x square plus beta x. We have been given time as alpha x square plus beta x. That's our time as a function of position. We have to calculate the retardation, or we have to calculate the acceleration, right? So what we'll be doing is that we have to calculate the retardation. It means we have to calculate t square x over dt square, right? Or dv over dt, right? dv over dt. So what we can do is that if we try to differentiate this equation on both sides with respect to time, differentiate on both sides with respect to time, we'll be taking the time derivative of this equation. So dt over t will be that will be equal to 1. So we'll be left with differentiation of x square with respect to time. That's going to be twice x into dx over dt, correct? Plus differentiation of beta x will be beta dx over dt, right? Correct. So from here, we'll be getting the value of v, right? So our value of v is nothing, it's twice alpha x dx over dt is nothing, it's v, and beta dx over dt is once again equal to v, right? We can get the v common from here, so v will be nothing. That will be equal to 1 over 1 plus 2 times alpha x, right? So this is our v, right? This is our v. And we also know that our acceleration is nothing. Our acceleration is nothing. We can write our acceleration it as in terms of position, in terms of velocity, in terms of position and velocity as well. We know acceleration, we write it as d square x over dt square, right? Or we can write it as dv over dt. And in the previous problem, we can also write it as v dv over dx, right? V d over dx. So this is also our acceleration, right? So we know v as a function of x, we can calculate the dv over dx, right? dv over dx, right? For dv over dx will be d upon dx of 1 upon 1 plus twice alpha x, right? So it will be nothing. It will be minus 1 plus twice alpha x to the power minus 2, right? And multiplied by twice alpha, right? So it means that will be left with minus twice alpha upon 1 plus 2 alpha x ka whole square, right? So this will be the derivative of this v with respect to x, correct? Now we will be substituting the value of this dv over dx in the equation. The acceleration is nothing, it's v dv over dx, and our v is nothing, it's 1 over 1 plus twice alpha x multiplied by minus 2 alpha upon 1 plus 2 alpha x whole square, right? So we'll be left with minus 2 alpha upon 1 plus 2 alpha x cube, right? So this will be the value of the acceleration or the retardation. We can see that the acceleration here is negative, right? It's a negative acceleration, right? Or we can say that it's a retardation in this case, right? So this is how we can calculate the acceleration. Through different means, we can calculate the acceleration by taking the double derivative of x with respect to time, or we can also calculate using dv over dt, or we can also use v dv over dx, right? So let's try to solve this last problem, right? Question number 8. The acceleration of a particle moving in a straight line varies with its displacement as a is equal to 2s plus v. Velocity of the particle is 0 at 0 displacement. Find the corresponding velocity displacement equation, right? We have to find the velocity displacement equation, right? We know that acceleration is nothing, it's defined as t square x over dt square, or we can also define it as dvx over dt, right? Or we can also define it as vx dvx over dx, right? So this is the component of acceleration along x-axis, right? Acceleration is given as a function of displacement s, right? We can write this acceleration as a is equal to, instead of s we'll be using x, that's 2x plus 1, right? Now we'll be using this equation because we have to find the velocity as a function of displacement, right? Then we'll be using this equation to calculate the velocity as a function of displacement. So we can substitute the value of a as v dv over dx, right? That will be equal to 2x plus 1, right? 2x plus 1. So v dv will be nothing, that will be 2x plus 1 into dx, right? Now we'll be integrating this. between the proper limits, right? We'll be integrating this equation on both sides between the proper limit. When the position of this particle, when the velocity of the particle is zero at zero displacement, when the displacement was zero, it means the velocity was zero, right? And after some displacement x, the velocity has become v, right? Velocity has become v, correct? So this will be the limit 0 to v and 0 to x. So the integration of v with respect to v will be nothing, it will be v square over 2 with the limits 0 to v, and the integration of this will be nothing, it will be 2x square over 2 plus x with the limits 0 to x, right? So it's nothing, it will be equal to x square plus x, right? X square plus x, and this will be equal to v square over 2 because the lower limit is equal to 0, right? So it will be equal to x square plus x, or we can say that our b is nothing, it's equal to 2 times x square plus x under root, right? So this is our final equation for the velocity as a function of displacement, right? Or as a function of position. And rest of the questions related to this or rest of the concepts will be discussed in the next lecture, right? And then next lecture will be discussing about some of the definitions like uniform velocity, non-uniform velocity, acceleration also. And we'll be also discussing about the different trajectories based on the acceleration, right? We'll be discussing the different types of trajectories based on the acceleration. So that was it for today. See you in the next class and goodbye.